Good day and welcome to another physics lesson. It is the continuation of our physics learning support program. Today we are going to be looking at the topic equilibrium of parallel coplanar forces. Parallel coplanar forces. This is the third video in the series that describes equilibrium of objects and the action of forces on such objects. You may like to see the previous two videos. They are on this channel. There is one titled Triangle of Forces. There is another titled Equilibrium of Forces, Stability of Objects. Both videos will go a long way in explaining the introductory aspect of this topic. And I implore you once again to subscribe to this channel, like the videos. If you have any questions, feel free to drop a comment and I'll definitely get back to you. So, to what we have today, equilibrium of parallel coplanar forces. Firstly, what do we mean by parallel coplanar forces? Coplanar forces just describe those forces that act together on the same plane, like on the same object. So for instance, if I hold this ruler, for instance, and there's someone else holding at the other side, if both of us were pulling the ruler towards ourselves, then we will both be exerting forces that are coplanar on this ruler, because they both act, the two forces being exerted by the two persons act on the same object, on the same ruler. Those are coplanar forces. What then do we mean by parallel? Parallel simply means two lines or two lines of action that do not meet. That is simple term of parallel. So let's look at this scenario. If we have, let's say we have a rod, and there's someone sitting here exerting a weight downwards. Let's call that person's weight W1. There's another person sitting here on the rod exerting another weight W2. The weight exerted by the two persons are forces, and they are acting on the same plane, meaning they are coplanar and they are parallel. Their lines of action will never meet. Even if I extend this arrow upwards here, it still will not meet. So that's essentially what parallel coplanar forces are. Now, for forces to keep an object in equilibrium, when the forces are parallel, there are two things that must happen, two conditions that must be met. I say again, for forces to act to keep an object in equilibrium, when their lines of action are parallel, there are two conditions that must be met. So we are going to look at, this is addressing the first objective now, conditions for equilibrium of parallel coplanar forces. Now, the first condition is that the sum of forces acting upwards on the object must be equal to the sum of forces that act downwards. So, if you have this object this way, say a rod or a plank, and then you have a force hanging down on it. Let's say you put a load here, or a brick, a block, something, you put it here. Okay, the line of action should be from the center, so let's extend it a little. Good. Yeah. So we have the weight of this block. Let's call that W. And then let's say the plank is resting on a support. That support, such as a pivot. By the way, this is a pivot, also called a fulcrum. So if we have this plank resting on any form of support that way, Then there is a normal reaction. There's a reaction between that support and the plank, and that reaction acts upwards. Let's call that one R, force R. And then let's say on the other side, there's another man, there's a man, say a mason, who is walking along the plank to pick up this block. So let's say the mason is here at this time. His own weight, let's call his own weight W naught. Now, what the first condition tells us is that the sum of upward forces must be equal to the sum of downward forces. So, these are downward forces, they are acting downwards. This is an upward force. So, from there, then R must be equal to W plus W naught. That's the first condition. Sum of upward forces acting on a plane or an object acting on a plane must equal sum of downward forces acting on the same plane. Acting on the same plane. Another way of saying this is to say the vector sum of both forces must be 0. Vector sum means you consider the directions. So if you consider the forces acting south as negative, the one acting north will be positive. By the time you do a vector sum, then you should have 0 as the answer. So that should give us something like, let's say these are southern forces. So let's say minus W. This is also another southern force, so plus minus W naught should be equal to R in very simple terms. Or if you like, you want to bring the R to the other side, then you could also write as minus W plus minus W naught. This is acting naught, so we want to use plus to denote that, plus R. Then everything should be equal to 0. Minus W minus W naught plus R should be equal to 0. That's vector sum. Now the second condition, that's the one that talks about the principle of moments. We call that the principle of moments. That's condition 2. Principle of moments. And that says that the sum of clockwise moments, about a point must equal the sum of anti-clockwise moments about the same point. Must equal the sum of anti-clockwise moments about the same point. So if you want to write this in simple terms, you want to write this long sentence, you just say clockwise moments equals anti-clockwise moments. At this point, we must understand what moment means. Moment is the product of a force and the perpendicular distance from the line of action of that force to a turning point. So if I want to take the moment of W naught here, for instance, if there's a distance here, let's call this distance from W to this turning point, let's call the distance X. Let's call it X, say in centimeters. So moment is this force multiplied by this perpendicular distance. Note the keyword perpendicular, not just any distance. Now, applying that principle, what is that saying? Let's look at a beautiful scenario. Let's say we have, say a vertical support or a wall, sort of, and then there is a support here, and there is a horizontal rod here. And then the rod has a weight. So let's say that the weight of the rod, which acts down from its center of mass or center of gravity, because I've used the term weight, let's say it is 50 newtons. And then let's say we have a thread that is holding this other side up to a ceiling to support that rod. If you have a thread, this is a thread. So let's call this force T1. T standing for thread. If the distance of the entire rod, let's give it a value. Let's give the distance a value of say 2 meters. Distance of the rod is 2 meters. And there's a thread supporting the other end of the rod to the ceiling, and there is also a turning point here about which this thread will go, maybe up and down. Now, if you are asked to calculate this, then what we use is the principle of moment. So in this case, we have to first of all identify our turning point. Our turning point, what we mean by turning point is essentially the point that an object can turn around or rotate about. So it may not necessarily go all the way around, but just for it to be able to rotate, go up and down about that point. So here, we are taking this as our turning point. So if this is our turning point, and we want to apply the principle of movement, then there's something here you must consider. Two key terms here: clockwise movement, anti-clockwise movement. Now the question you will ask yourself is, how do I pick a clockwise movement? How do I pick an anti-clockwise movement? It's easy. Just draw a clock somewhere by the side. You know what the clock looks like. You have the 12 here, the 6, and then you have the 3 and the 9. And the hand of the clock moves this way. The hand of the clock moves the other way. This way. So any direction like that, any continuous direction that goes this way, that will be clockwise. This will be clockwise. On the other hand, if you draw a clock again, you have your values 12, 6, 3, 9, and you have a direction going this way. Not that the clock can turn back, mind you, but let's imagine that you have a force that is acting in this direction. Then this is simply the anti-clockwise direction. This is anti-clockwise. So this will guide you to know which is clockwise and which is anti-clockwise. So now let's apply that. This is our turning point. So we want to assume that these forces are trying to rotate towards the turning point. It's an assumption, not that they actually rotate, but for us to be able to apply that, that's a simple thing to do to understand it. Assume that this force is rotating to come as if it was coming here, and this is rotating as if it was coming here. Now, which of them will go clockwise? Let's see. This black one will have to move this way. If you look at that direction, it tallies with this. So this is clockwise. And if you look at the other one, if this was to move this way, it will go anti-clockwise. So this is anti-clockwise and this is clockwise. Now, moment, as I said, is force times distance. So that will mean, because this mass or this weight is acting at the center, so we can then assume that the distance from here to here is 1 meter. This is at the center. Then we are able to apply a formula. Clockwise moment, that's 50 times 1. Moment is force times perpendicular distance, don't forget. That will be equal to T1 that we are looking for times 2. And if you do this, your answer is very simple. That gives you 50 over 2 equals T1. And your T1 is equal to 25 Newton. So that's a very simple way of applying clockwise movements, irrespective of how complex the diagram may be. Let's say you even have a diagram that has so many forces on it. such as this. Let's say this has a support here. It has a support here. So there's a reaction here. Let's call that R1. There's a reaction here. Let's call that R2. There is a weight, the weight of the object itself. Let's call that W. Let's say you hang a mass, a certain mass. Let's call that M1 here, M2 here. And there are distances. Let's call this distance X1, this distance X2, this distance X3, this distance X4. Whatever it is you are looking for, all you need to do is just to determine a point about which you will take your moment. So you could take a moment about this point, for instance, this very point C. And then you just treat every other force as if they were coming towards that point. That way you'll be able to determine which is clockwise, which is anti-clockwise. In rounding off, let's just see, for demonstration, R2, if R2 was moving towards R1, R2 will move this way. W will move this way. M2 will move this way. They were moving towards point C, and this will move this way. If you look at this is going anti-clockwise, and so it is. So M1 and R2 are anti-clockwise. W and M2 are clockwise. We have ignored R1 because that is where we are taking our moment about. So you ignore the force at the point you choose as your turning point. And this way it is easy to solve any such questions. So I believe that this has put a bit more clarity on this topic. If there are any questions, don't forget to drop a comment and I'll get back to you. I'll see you in another video shortly.